you will have heard about by the end of this unit. Okay, and these genes are P21. Okay, you heard of this one? Yeah, this is the CDK inhibitor under stress conditions. So this is how we get P21. P53 activates the P21 gene. It's the P21 gene. It's the most famous gene that P53 activates. It's also the protein, the gene P21 has also been used in cancer gene therapy. MDM2, which you might not have heard of yet. Okay. Bax, APAP, Puma, Noxa. Bax, APAP, Puma, and Noxa. I think people in the biochem haven't heard of APAP because we just looked at gene expression of APAP. Okay, these are proapoptotic proteins. Okay, Bax and APAP are actually involved in apoptosis. Puma and Noxa are regulating apoptosis. They're regulators of apoptosis, but Bax and APAP are some of the I want to call it executioners, but they're the players, apoptotic players, regulated by Puma and Noxa. Okay, MDM2 is a ubiquitin ligase. We're going to see that in a little bit. M stands for, the first M stands for mammalian. So sometimes you see, if you're talking about the human gene specifically, you might see HDM2, and the H means human. Okay, ubiquitin ligase. P21 is a CDK inhibitor, and we're going to just assume, we're going to call it a CDK2 inhibitor. Okay, another substrate is MDM2. Okay. And this, I'm just going to say inactivates it. And I'm kind of lying. Just saying activates. Okay? And I'll come back and tell you why I lied. Okay, so I put MDM2 next to P53 for a reason. It turns out that MDM2 can bind to P53. There's a part of, near the N-terminus, a region of P53 that is a docking site for MDM2. Okay, so we get these two proteins together. Okay, and if MDM2 is a ubiquitin ligase, what do you suppose it's going to do to P53? Yeah, it's going to polyubiquinate P53. And that's going to lead to the destruction of P53.
The not phosphorylated.
Huh? yes,
MDM.
because the phosphate groups, I'm guessing it's the non-phosphorylated, the phosphate groups that, like this one and other ones, I'm gonna add another phosphate group in a little bit. The phosphate groups are in the MDM2 binding site, so I think it does, MDM2 does not bind to phosphorylated P53. Okay, so P53. Okay, so why do you suppose P53 turns on the MDM2 gene?
To stop apoptosis?
Yeah, so this is like a negative negative feedback, okay? So MDM, so like a lot of things, like MYC also turns on CDK inhibitors, but P53 also turns on the gene that ends the signal, okay? So it turns on a gene that really leads to the demise of P53, so we're gonna call this negative feedback. That's how you get rid of P53 when it's done, or get rid of most of it. Negative feedback. And we get that. Okay. There is a way to rescue P53, or another way to rescue P53. One way is, well, phosphorylate MDM2, and then you can get rid of MDM2 activity. Here's why I'm kind of lying to you, and I don't care if you remember this or not, it's not important. MDM2 will, when it's phosphorylated, monoubiquinase P53, but it can't polyubiquinate P53, so that doesn't lead to P53 destruction. So let's just say it's inactive because it cannot result in P53 destruction. Okay, but let me tell you another way we can rescue P53 from MDM2. Okay. I'm going to just put MDM2 over here. In my notes it says this is all together, but this is getting crowded on the board. Active. And we can inactivate it. MDM2 inactive by a cool protein ARF. Okay, remember you've heard about ARF. Okay, it's coded for by the same gene as P16. So MYC turns on ARF, and anything that turns on the P16 gene is also going to turn on ARF. Okay, ARF binds to MDM2 so that P53 can't bind, that MDM2 can't bind to P53. Okay, so this inactivates MDM2. It cannot interact with P53. Okay, I'll put that. How are we doing on time? Okay.
Does ARP have anything to do with ATM?
No, it really doesn't. No, so this, it really has no, it's coming from MYC gene activity or whatever, ELK gene activity or E2F gene activity. Okay, so ARF rescues P53 from demise by MDM2. That's probably the best way to describe ARF's activity. Phosphorylation of MDM2 by ATM also rescues P53 from destruction, okay, by MDM2. So we got a couple of ways of knocking out MDM2. Would you classify MDM2 as a tumor suppressor gene or an oncogenic protein? Is it a tumor suppressor protein or oncogenic protein? too much MDM activity would, huh? Too much MDM activity would do what?
It would make the cell cycle.
Probably lead to the loss of P53. The loss of the ability to respond to, is it safe for me to divide? No. If you have too much MDM2 activity, the cell might be able to determine that it's not safe to divide, but the cell doesn't have much can't respond to the answer. Okay, so we got a couple. All right, I think we have time for another. This is a cool one. Well, the downstream consequences are cool. This protein is not cool, but the downstream consequences are cool. Okay. Okay, so you see a K in there, so you're thinking kinase. This is checkpoint kinase 2. At least that's what I call it. Okay, and it is active in the phosphorylated form. Okay. And one of the things it will do, one of its substrates is P53, so it puts another phosphate on P53 in the region that MDM2 binds to. So here, we'll put this. Okay, but that's not the important substrate. It just happens, that happens, but that's not the important substrate. Here is the important substrate. Are you ready to go on? And picking up and being put down. Pick up and being put down. Okay, here's the important substrate. What does CDC25 do? Yeah, it removes the inhibitory phosphates from CDK2. Okay. Checkpoint kinase 2, or CHK2, phosphorylate CDC25. Is that going to enhance, that phosphate group, will that enhance the activity or inhibit the activity? Okay, so CDC removes inhibitory phosphates. Is going to actually, it sounds like, oh, if you don't want the inhibitory phosphates to be removed, we better make CDC inactive. Okay? So actually what happens once CDC is phosphorylated by checkpoint kinase 2, it becomes ubiquitinated and destroyed. Simple as okay, we've just lost the ability to remove the inhibiting phosphates. And keep the CDK2 inhibited. Yes.
So does that phosphate go on a specific place on the protein that says that it's ubiquitinated? Or when
They always do.
okay, so anytime CDC25 takes an inhibitory protein off, is it ubiquitinated?
CDC25 takes off inhibitory phosphates, not protein.
Yeah. I was saying if so by putting that phosphate on, is it in a specific place on CDC25?
Yes. Oh, yes.
Okay.
Yes.
So when CDC25 takes the phosphates takes the inhibitory phosphates off, is it also ubiquitinated?
It doesn't put the
No.
phosphates on.
No,
I just take
the
them
source
off.
of
Okay.
phosphates coming from the kinase. And the kinase always gets the phosphate group from ATP. It's not moving a phosphate. So when CDC is a phosphatase, it doesn't transfer phosphate from the CDK2 to CDC25. It just takes off.
Okay.
So does that mean like proteins like PPP make ATP?
No, wouldn't that be nice? You would, this is sort of a futile cycle. Okay, so let's just use, here's a protein. And it gets phosphorylated by ATP, but always the phosphatase comes off as inorganic phosphate. So we would call this a futile cycle because you could just keep going around and around and around. All you're doing is burning off ATP and you're not regenerating ATP. Well, it may not be futile, in fact, because you get whatever cellular response, but there are some steps in glycolysis that are futile cycles in this way. You just keep phosphorylating, dephosphorylating, phosphorylating, dephosphorylating. And people who can eat a whole lot and not gain weight, anybody know it? Do a lot of futile cycles in glycolysis. So we had a friend when we lived in Champaign-Urbana, who could eat more, who could just eat unbelievable amounts of food and he never gained weight. I bet he had a lot of futile cycles going on. So I always think of him when I think about futile cycles. There's a guy who wasted energy like crazy. Okay. All right, so we've just rendered, checkpoint kinase 2 puts a mark of death on the CDC25. Ubiquitin ligase recognizes that phosphate, binds to that phosphate, and CDC25 is ubiquitinated and destroyed. So, what that means is, this also could be A. It doesn't really make any difference whether it's cyclin B or cyclin A. So cyclin CDK2 keeps its inhibitory phosphates. Even if cyclin E is bound to CDK2, it's not going to be active because of the inhibitory phosphates, which I believe is at the mouth of the active site of CDK2. So you can't get substrates to bind to CDK2. Okay, so this is what, so now the CDK2 is stuck in this form. Okay, because we just inactivated CDC25, not only inactivated, we destroyed CDC25. And if that wasn't enough, now we got B21. Which is going to bind to CDK2 and inhibit CDK2 activity. So we got a couple of ways of getting rid of CDK2 activity, even if cyclin E or cyclin A is present. Okay, those two events can override the presence of cyclin E or cyclin A. So even if the cell has started to cycle, the chain of events that is initiated by DNA damage, pretty much inactivates CDK2. So you're gonna see the cell not progress into S phase. Or sometimes the cell just stalls in S phase. And I think and that can result in apoptosis. Okay, I got one more substrate, and I'm not going anywhere with it, and I'll just tell you what the substrate is. Oh, then we'll summarize. Then we'll summarize what all happened. Okay. Okay, BRCA1, what is that? Who's heard of BRCA1? Yeah, breast cancer antigen. Okay, that is mutant, quite often mutant in inheritable forms of breast cancer. Does that involve most breast cancers or less than half, or what's the abundance of inheritable?
I thought BRCA2 was the one that was more popular.
It might be, but if you combine BRCA1 and BRCA2, what percent of breast cancer patients have mutant BRCA1, BRCA2? Actually, probably closer to 10% or less. Most breast cancers are not inherited; they're sporadic. But if you do, BRCA1, okay, is a substrate for ATM. Okay, and the phosphorylation activates BRCA1, and its main job is to recruit inhibitory protein, and that's probably why it's probably not all that well understood. DNA repair enzyme. To the site of the DNA damaged areas. How would the loss of this protein be associated with cancer then?
Because it's not fixing DNA damage.
Yeah, you can't fix mutations without, so a lot of mutations will persist in the genome if you don't have a functional BRCA1. Okay? Does everybody with a BRCA1 mutation get breast cancer or some other kind of cancer? No, because it takes knocking out the other gene. So you inherit one mutant BRCA1 gene from one of your parents, and then you have to knock out the other gene generally by silencing that gene through DNA methylation. And under those conditions, that leads to breast cancer. Okay, so let's summarize. I was gonna, then Friday we'll talk about how else. So if you have a mutant P53, all you need to do is mutate one of the two genes. Okay, so unfortunately that's pretty easy to do, because functional P53 requires 4 active proteins. Okay, so you have to have a tetramer made up of 4 active proteins. So what ratio of tetramers would be active? If mutant P53 and normal P53 bound to each other with equal affinity, okay, what ratio, I'll say how many tetramers would be active? Okay, so okay, tetramer, we'll think about a single tetramer. What's the chance that member 1 in the tetramer is active? And what's the probability that it's inactive? Let's say, what's the probability that it's going to be active? Yeah, 50-50, right? If there's one normal gene, one mutant gene, then they're both equally expressed, okay? Which may or may not be true. Okay, what's the probability that protein number 2 of the p53 tetramer is active? Okay, and the probability that member 3 of the p53 tetramer is active is? And the probability. Okay, so this is assuming a lot. This is assuming that both genes are equally expressed, and there's that mutant protein and normal protein both bind with equal affinity. About 1 in 16 tetramers would be active tetramers. Okay, so all you have to do is mutate one of the 2 p53 genes to lose functional p53 activity. Okay, so here's what we've seen so far with p53. We've seen that it will lead to cell cycle arrest. Okay, DNA damage through ATM also leads to cell cycle arrest. Okay, hang on, we will see these proteins involved in apoptosis. Okay, and DNA damage also activates really a lot of DNA, some DNA repair. So ATM is going to lead to cell cycle arrest through CDC destruction and P21 formation. DNA damage is going to prime the cell for apoptosis, okay, because we'll see an increase in these gene products. And DNA damage will activate the recruitment of DNA repair enzymes to the site of damage. Okay, so I think so next time we'll take a look at, so how do we, if a cell has normal p53 genes, how can you still knock out p53 activity? Okay.
Because you only need one to be.